All right, today we're going to be looking at circular motion. Our objective is to be able to analyze the motion of an object moving in a circular path to find its centripetal force and centripetal acceleration. So we have 2 points here, A and B. Which one is moving faster? Actually, it depends. Are you talking about tangential speed or circular speed? Angular speed in this case. That's what circular speed is. It has angles, so it's circular. Okay. So linear speed is just the regular speed. We're talking v equals d over t here for linear. And the outside of the disk has a greater speed than the inside because it has a greater distance. So this is called the tangential speed. Rotational speed or angular speed is how many rotations occur in 1 minute or second, whatever your time is. Per minute is abbreviated RPM. You may have heard that before. So tangential speed increases as you move out from the center, but rotational stays the same. Uniform circular motion has the same speed but not the same velocity. As you go around the circle, you are keeping the same speed. It's still going, say, 2 meters per second if you have a circle that's 2 meters in circumference, but the direction is constantly changing. So your velocity is changing. The period, this is what it's called for the amount of time it takes to make one rotation. So how much time it takes for one cycle. So you could say 1.3 seconds for one cycle. And the unit for a period is a second, whatever your time is, but a second is the SI unit. Frequency is how often it circulates per second or per minute. So the units are 1 per second, and the symbol is Hz, which is hertz. Like the car company. Okay, so if you said 25 cycles per second, that would be equal to 25 hertz. And now frequency is the inverse of period. So if they give you period and you need frequency, it's just 1 over period. And if they give you frequency and you need period, it's 1 over frequency. So for example, the 25 cycles per second, this is 25 hertz. This is the frequency. If you need period, period is going to be equal to 1 over 25 seconds on the bottom, and 1 over, not seconds, this is hertz, 1 over 25 hertz, and that's equal to 1 over 25 seconds then comes up on the top. Okay, you can plug in 1 divided by 25, and whatever that is then the seconds. Okay, so for an example, here's a chart. If you did 30 hertz, it would be 1 divided by 30 hertz, and you get 0.03 seconds. Down here, you could, for frequency, you could have 1 divided by 0.2 seconds, and that is equal to 5 hertz. So the period, the unit is seconds, and the unit here is hertz. So in your calculator, if you use x or times 10 to the EE, you will be off by an exponent of 1. What you need to type in is actually, if you're trying to say 2.4 times 10 to the right, 2.4 EE 5, and that is equal to 2.4 times 10 to the 5th in your calculator. And we'll practice this in class. Okay, so here's a joke for you. Capital M is mega, megahertz. Okay. All right, so then we have linear speed, which we've talked about before, v equals d over t. Circular, though, comes from linear speed. You can derive it from that. You can figure it out. So what's the actual distance it's traveling around? Well, that's the circumference. And that's equal to d. So the distance is 2 pi r. This is in your reference table. So then the period is t, capital T. So if you need the velocity, the angular velocity, it's equal to 2 pi r divided by t. So when moving in a circle, the velocity is at right angles to the radius or at the tangent to the circle. So the velocity is always tangent to the circle like this. So this is a right angle to the radius. And so you can see you can add these as many times as you want. And this is the velocity, okay? So then if you look at this, velocity is always changing. So if you have an always changing velocity, if you remember, means that you have an acceleration. It also means that you have a force, because if you remember, F net equals mass times acceleration. If there's an acceleration, you must have a force. So if you suddenly make the force go to 0, the object goes in a straight line. So if you're going around your circle, if you let go, it'll go straight off of that circle, tangent to the circle. So when driving in a car, when you make a turn, you get thrown to the outside because that's how you want to keep going. It's inertia. Your inertia is in motion and you want to keep going, but the door gets in the way. So that's why you get thrown to the door, because you want to, the car is moving and it's going, but you want to stay where you're going in the direction you're already headed, but the door gets in your way. Okay, so in order for velocity to constantly changing, just as I said, there must be an acceleration. Just as I drew before, the acceleration is at right angles to the velocity. So the velocity is at right angles to the acceleration, but then you have, so that's velocity. Then you have right angles to the velocity, and the acceleration is always pointed in. Toward the radius. I guess toward the center of the circle, actually. Okay. If the acceleration had any components in the same direction as the direction of motion, there would be, so it would either speed up or slow down. So it would make it so that it's no longer moving in a circle. It's adding to the velocity that's already there, or subtracting. So it ends up going in a straight line and adding to the speed that's already there. All right, so then just a little bit on vocabulary. There's centripetal versus centrifugal. Centripetal acceleration is the inward acceleration or circular motion. That's how it has to be in order to be centripetal. In order to be moving in a circle, it requires a force pulling toward the inside to create that circle, circular motion. You don't actually have anything moving to the outside. That outside force is not really a force. It's just inertia trying to keep the object in motion. So then we have our equation. It's the centripetal acceleration is equal to v squared divided by r. This is in your reference table. the centripetal acceleration is a sub c, v is the tangential velocity or speed, and r is the radius. So as you can see, if you have a small radius, you'll have a big acceleration, centripetal acceleration. If you have a big radius, you'll have a small acceleration. So here, as the velocity increases, the acceleration also increases, and that it's going to increase actually exponentially based on that polynomial. All right, then the centripetal force, this is also in your reference table, is equal to mass times centripetal acceleration. So you can see that as the acceleration increases, you have a direct relationship with the acceleration. So as the acceleration increases, so does the force. It's directly related. So you can see that here in the equation, as one goes up, so does the other one. So here's just a quick sample problem. What is the centripetal acceleration of the 1.5 kilogram cart on a track that is 1.3 meters in radius and has a 2 meters per second velocity going around? So then we can just use our equation. Centripetal acceleration equals v squared divided by r. You plug in, and you get centripetal force is equal to mass times centripetal acceleration. It's equal to 1.5 kilograms times 3.1 meters per second squared, and you get 4.6 kilograms meters per second squared if you work it out, and that's equal to 4.6 newtons. It is a force, so newtons is the unit we want. All right, thank you.